All right, today we're going to discuss section 4.1, linear functions and their properties. The first objective for the section is we're going to graph linear functions. Technically, you've graphed linear functions in the past, and in chapter 2 we did a review of graphing linear functions. Usually we write the equation for a linear function as y equals mx plus b. But because we're talking about functions specifically now, we're going to replace the y symbol with f of x and say f of x equals mx plus b. So remember from a prior conversation on graphing lines that you should have seen at some point in your past, right? Or if you go back and look in chapter 2, the slope is the coefficient of the x variable here. And we denote that with the symbol m, right? But remember, this is a number. And then the y-intercept we denote with the symbol b, would be, again, 0 comma b as an ordered pair. So, quick review. If we had graphing the linear function f of x equals negative 3x plus 7, so back in chapter 2, the way we could graph this pretty quickly is we could plot the y-intercept. So we have the y-intercept of 0, 7 here. And we could plot that point here, 0, 7. And then we could use the idea of slope to plot infinitely many more points. So since the slope is negative 3 divided by 1, what I'm going to do is do a rise over run. So I have a rise of negative 3, which technically is a fall, right? So I'm going from this point, I'm moving over 1 unit that's in the denominator, and I'm going down 3 units for my fall. And it gives me the next point 1, 4. Another way you could graph a line, right? You could just plot 2 points. So I could pick x equals 0, and I would get y equals 7, and we can see there's that point. And then I could just plug in x equals 1, and I would get negative 3 plus 7, which is 4. That gives me that next point. Now, the nice thing about this little example here is a quick reminder of what slope does for me, right? The slope is rise over run. So I have in the numerator here negative 3, and in the denominator that really isn't visible, I have a 1 sitting there. Now also real quick, just to remind you, right, if I was going to use graphing technology, so let me bring up an old school emulator here. So if I was going to graph on a calculator, right, I'm going to hit the y equals button. And once I hit the y equals button, I'm going to be able to type in, I'm going to use the negative symbol here, negative 3, and then I'll hit the variable button, x, and then I'll say plus 7. And if I hit graph, let's see what window I'm in. Remember, I could always go to zoom button and choose zoom standard, number 6. I'm going to punch zoom 6, and that brings me to the standard viewing window, and we can see that matches the graph that we have here. And we could also graph with the free web-based calculator, Desmos.com. So if I just go to Desmos.com on my web browser, or I open up the free app that I have on my phone, right, we could click the Start Graphing button. And once the grapher loads, then we can just type y equals, and we had what, negative 3x plus 7, and it'll graph that line for me. Right? Now, what I love about the Desmos grapher is I can just kind of click and drag the window here, right? I can highlight certain points that I might want to see on the graph, right? I can even click and just kind of hold my button and pull a point down. I could go right to where x equals 1 and see that the y is 4, and suddenly my browser's freezing there. Oh, there we go. I could see where x is 1 and y is 4. All right. So since we can talk about graphing, right, with our graphing technology, either with a web-based calculator like Desmos or our handheld calculator like a TI. Of course, we can graph lines by hand as well, right? So if we took away all of that technology, we could easily graph the line by plotting 2 points or using the slope, rise over run, to sketch the line. The technology is wonderful. We're definitely going to use it, but it's not really necessary in this case. All right, so let's talk about the average rate of change. So what average rate of change is basically is just a new term for the slope, right? So for example, let's take our equation that we had from that prior slide, and let's look at negative 3x plus 7, right? And if we think of building a table of values, right, over here on the left we have a table. So if I plug negative 2 into the equation, excuse me, I'm going to get negative 3 times negative 2, which is positive 6, plus 7, which is 13, and so there's that first point. If I plug negative 1 into the equation, I'm going to get negative 3 times negative 1, which is positive 3, plus 7, which is 10. There's that next point. So if I were to just plug some x values in to the equation and fill out the y values, right, the function values, here's what a table might look like for that graph. And then if we look specifically numerically, right, so let's talk about the slope, right? So again, slope being change in y over the change in x value, right? So we're going to, between these 2 points, we're going to find the slope. So I'm going to take the change in the y values. So the way that we're setting this up is we're doing this y value minus this y value. So we got 10 minus 13 in the numerator. And if we do 10 minus 13, then we have to subtract the x's in the same direction. So if we do 10 minus 13 in the numerator, then our change in x would be negative 1 minus 2. So negative 1 minus 2 gives me 1 in the denominator, and then there's my slope of negative 3 that we already know that we have. Right? So we're just connecting to a prior example here. If I grab these 2 points and I find the slope, again in the numerator I'm going to do change in y, so I'll do 7 minus 10 in the numerator, there's 7 minus 10, and in the denominator I'll do change in x, I'll do 0 minus negative 1, which is 0 plus 1, which is 1. So we get negative 3 over 1, which is negative 3 again. Right? And if we were to continue that, right, if we were to do 4 minus 7, that would be negative 3 in the numerator over 1 minus 0, which is 1 in the denominator. So we're getting the same slope. So here's the new idea here. So graphing lines is not new, right? But what's new here is we're going to attach the idea to slope that we call average rate of change. So the average rate of change literally is how does y change in relation to x. We're going to call that the rate of change. And for a line, that average rate of change is always the same value. So what we're going to notice for a line, and let me go back to that prior slide, we're going to notice for a line is at any 2 points on the line, there's going to be the same slope between those 2 points. If I were to pick a point at 1, 4 and pick a point at x equals 2, right, that's the same slope there. So the slope is always the same. So we're going to call that, this slope is always the same, negative 3, we're going to call that a constant rate of change. Right? So lines have a constant slope. The slope is the same between all the points. Right? Again, here's the formal definition. Right? We're going to call the average rate of change what we've been calling the slope all along. And for a line, right here, we say the line has a constant rate of change. Right? So here's a quick kind of word problem to maybe make some sense of this. Right? So let's say we have a strain of E. coli bacteria and it's placed into a petri dish at 30 degrees Celsius and it's allowed to grow. So the data shown in the table below, right, table 2, represents the population as far as measured in grams, and the time is in hours. Right? So let's plot the ordered pairs in the XY Cartesian plane, and let's use the average rate of change to determine whether this function is linear or not. So first of all, real quick, let me just discuss with you guys what may or may not be obvious. Notice that we're letting time be the x value, right? So in this case, time is independent. All right, so that's why we're letting it be the x value. And then the population is the y value. So remember, the y value is always dependent variable. The x value is always the independent variable. So we're going to think of population as being dependent upon the time, right? As time progresses, the population depends upon that progression of time. The more time that passes, the more population that we typically have. So that's why we're setting the table up in this fashion, right? The hours are the independent variable, the population is the dependent variable. So here's a table of data given to us from the scientists. And if we were to go to the next screen here and let's say plot that table of data, if we were to be real specific about plotting that table, here's what that table of data looks like. And just real quick by eye inspection, right, we can see that it doesn't really look like a line is going to fit this. Right? If I plot a line between these 2 points, then it's going to veer way off of the points at the top. And if I plot a line between these 2 points, then it's going to veer way off of the points over here on the far left. So this doesn't appear to be linear, but let's be a little bit more specific about this, right? So let's find the slope between all pairs of points. So if I grab these first 2 pairs of points, I do 0.12 minus 0.09 divided by 1 minus 0, I get a slope of 0.03. And if I grab these 2 points here, I do 0.16 minus 0.12, and I divide by 2 minus 1, right? So I'm doing change in y over change in x. I get a slope of 0.04. And then if I do these 2 pairs of points, I do 0.22 minus 0.16 in the numerator, divide by 3 minus 2 in the denominator, I'm going to get a 0.06. So if I find slope between all pairs of points here, notice how the slope is changing. It's not constant. It's not always the same slope. Between these 2 points, the slope is 0.03. Here it's 0.04. Here it's 0.06, 0.07, 0.10. So the slope is getting bigger, and we can see that visually, right? Here the slope was 0.03. Here the slope is 0.04. Here the slope is 0.06. 0.07, 0.10. So we can see between successive pairs of points, it's getting steeper and steeper. So we're going to say that this is not a constant rate of change, therefore it is not a linear function, right? Another example, right? So the data in Table 3 represents the maximum number of heartbeats that a healthy individual should have during a 15-second interval of time while exercising for different ages. So it says plot the ordered pairs in the xy Cartesian plane, right, and use the average rate of change to determine whether the function is linear. So for a particular age, we have numbers of heartbeats. Right? Again, excuse me, the age is the independent variable. The heartbeats are dependent upon your age, right? So we can kind of see from this data here that the younger you are, the smaller your heartbeats, right? Looks like the heartbeats actually are getting slower and slower over time. It looks like the heartbeats are decreasing. So we're starting out with 50 and we're getting smaller. So let's see if this data is really linear or not, right? So we can see from this, if we plot the data, it looks like it's relatively linear, right? But again, we shouldn't just use the graph. We should find the slope. So let's go ahead and find the slope. And if we find the slope between these 2 pairs of points, 47.5 minus 50 over 30 minus 20, we're getting a slope of negative 0.25. And if we find the slope between these 2 pairs of points, change in y, 45 minus 47.5 over 40 minus 30, I'm going to get negative 0.25. So if I were to continue to find the slope between all pairs of points, I'm going to see the slope stays exactly the same. So we have a constant rate of change. We have a true linear data set here. And again, notice that behavior that we saw is it looked like the heartbeats were getting lower as age increased. All right? Okay, so the last thing we're going to do here in this section before we look at a couple word problems is determine the ideas of increasing, decreasing, or constant. Right? So obviously if I'm increasing, my graph is going upwards from left to right, kind of like we're showing in the lines here. If I'm decreasing, my graph is going down from left to right. And if I'm constant, it's staying the same. Right? So a linear function, right, is increasing if its slope is positive. It is decreasing if its slope is negative, and it's constant if the domain, over the domain if the slope is 0. So we're just talking about the shape of the line here, right? So just the review from 2.3 says that same thing, right? It says if a line has positive slope, then it's increasing. If the line has negative slope, then it's decreasing, right? If a line has no slope, then it's horizontal, right? And thus it's constant. So if we look at these examples here, if we look at letter A, we can see this line, mx plus b. This line has a slope that's positive, and therefore it must be increasing. We could pretty quickly plot 2 points there, or we could just graph on our calculator. Right, so if I punch in 5x minus 2 on my calculator, I could pretty quickly see from that graph that it's increasing, right, as we would expect. We see letter B down here, the slope is negative 2. So we know that line should be decreasing because the slope is negative 2. Let's go ahead and plug it in our calculator and graph it. We can see that that line is definitely decreasing, right? Here's letter C. The slope is positive 3/4. so I know that that line should be increasing. Right? So in my calculator, I'm going to hit the clear button. I'm going to put parentheses, say 3 divided by 4, and close the parentheses. So there's my slope, 3/4 x minus 4. And even though the variable here is t, remember my calculator doesn't care, right? My calculator is going to use the x variable. So I'm going to get the same exact graph, whatever my variables are there, right? So there's my line increasing with a slope of 3/4. And then here's a line y equals 7, right? So that's going to be a horizontal line. Let me hit clear. Graph y equals 7. There is no slope to that line, right? And it's horizontal, right? It's constant. Okay, so we shouldn't need the graphing calculator, right? That's the whole point of this conversation. If I were to ask you a question, does this line increase or decrease? You shouldn't need to take your graphing technology out. I should be able to look right at the equation and say, slope is positive, it's increasing, or slope is negative and it's decreasing. So let's look at our last example here where we have an application. Right? So in this application, we're going to talk about depreciation of the value of a car. So the problem says that the book value is the value of an asset that a company uses to create its balance sheet. Some companies depreciate their assets using straight line depreciation so that the value of the asset declines by a fixed amount each year, right? A constant rate of change. The amount of the decline depends on the useful life that the company places on the asset. So suppose that a company just purchased a fleet of new cars for its sales force at a cost of $28,000 per car. The company chooses to depreciate each vehicle using the straight line method over 7 years. So what this means is each car will depreciate by, so we have our $28,000 total value. We're going to divide by the 7 years we have. We're going to depreciate it $4,000 each year. So that's like our slope. We have $4,000 per year. That's our rate of change. We have our change in value over our change in years. And there's our slope, right? So letter A says write a linear function that expresses the value of each car as a function of its age x. So we have our slope of 4,000, and it has to be a negative 4,000 because we're decreasing the value of the car, right? It's depreciating. And then we have our original value of $28,000. And again, if I bring up my calculator real quick and I were to graph this equation, all right, so I plug the equation in and I hit graph, right? And obviously, if you think about this real quick, right, I'm not really going to be able to see this line very well based on the window that I'm in because the slope is negative 4,000. That's huge. And the y-intercept is 28,000, right? So if I look at my y-axis, I go up to y of 10. I don't have a y of 28,000, right? So I think what I'm going to do here real quick is instead of using the zoom standard, I'm going to use the zoom fit feature. So I'm going to choose zoom and I'm going to punch the number 0. And it should fit the graph a little bit better. And it is a little bit better of a representation, right? Now I should be able to hit trace and punch the number 0 and hit enter, and I can see there's my y-intercept, right? So my car, right, at year 0, right when I buy the car, it's 0 years old, its value is $28,000. So there's, the interpretation, let's say, of my y-intercept. My y-intercept shows me that the car's value when it's brand new, 0 years old. And then we're going to depreciate it $4,000 every year. And at the 7th year, we're saying the car is worthless to us, right? So if I trace and punch 7, that's going to be, my x-intercept there. So after 7 years, I've said the car has 0 value. We've depreciated the car over those 7 years. All right, let's answer the couple questions we have here formally, right? So letter B says graph the linear function, right? I already did that on the graphing technology. But if we do this by hand, right, I'm going to plot the y-intercept here, and then I'm going to depreciate 4,000 each year until I get to year 7 where the vehicle has no value. So I can very easily by hand plot the value of the new car, plot the value of the 7-year-old car, and there's my line that plots the relationship between value and years. So let's see letter C ask us, what is the book value of each car after 3 years? Right? So that's a pretty easy question to answer, right? We're just going to take 3, plug it into our x value, and find the value of the car. So if I plug 3 into the equation, Right? Function notation, we're going to say V at 3 equals. When I plug 3 in, I'm going to get $16,000 for the value of the car after 3 years. All right, so letter D says interpret the slope. And we kind of already talked about this, but let's make it a little bit more formal. Right? So we're saying that the car will depreciate by $4,000 per year. Right? So every year that goes by, the car will lose $4,000 in value. And again, remember, there's kind of an imaginary 1 here in the denominator. I got negative 4,000 over 1. So we're saying every year that goes by, every increase of 1 year, we lose 4,000 in value because the slope is negative. All right, and letter E says, when will the book value of each car be $8,000? So in this case, I want to point out to you, right, what we're giving ourselves here is the value of the car, and we're trying to find the year X in which we achieve that value. So we're setting the value equal to 8,000, and we're finding the year X in which that happens. So here I took the value, the Y value, I set it equal to 8,000, and I'm solving for X. Right? So what I did here is I added the 4,000X to this side, and then I subtracted the 8,000 to this side, and I got to this line. And then I divide both sides by 4,000, and I get X equals 5. Right? So we're going to say that after 5 years, we'll have a value of $8,000. Okay, guys, let's take a look at this last example. We're going to talk about supply and demand. So this problem says that the quantity supplied for a good is the amount of product that a company is willing to make available for sale for a particular price. The quantity demanded of a good is the amount of product that consumers are willing to purchase at a given price, right? So demand is how much I'm willing to buy, right? And supply is how much a company's willing to make. So suppose that the quantity supplied S and quantity demanded D of cellular telephones each month are given by the following functions. So here's particular equations given to us. So the supply equation is linear with a slope of positive 60. The demand equation is linear with a slope of negative 15. And P is representing the price of this quantity, all right? Right, so in this case, we're talking about prices of cell phones, right? So if the cell phone is sold for P dollars per phone, then the supplier is willing to supply based on this equation. And if the price of the cell phone is sold, again, at P dollars per phone, the demand is described given this equation. So letter A says the equilibrium price of a product is defined as the price at which quantity and demand are equal. Right? So the equilibrium price is the price at which S equals D. So part A is saying find the equilibrium price for this particular model. So what I'm literally do is going to take those two equations, I'm going to set them equal to each other. So if I set those two equations equal to each other, I get 60p minus 900 equals negative 15p plus 2850. And if I solve, right, the way that I solved this was I added 15p to both sides, and it gave me 75p. And then I added 900 to both sides, and that gave me 3750. Then I divide both sides by 75, and I get p equals 50. So the equilibrium price is $50. So if I charge $50 per cell phone, that's one heck of a cheap cell phone, I tell you. If I charge $50 per cell phone, then the model that we have here is in equilibrium, right? In other words, that means supply and demand are at the same quantity if I charge $50 per cell phone, right? So to find the equilibrium quantity, right, then what I'm going to do is plug it into either one of these equations. So I could take $50 and I could plug it into this first equation and find what the quantity supplied is, right? Or I could take P equals $50, plug it in the second equation and find what the quantity demanded is. I chose the supply equation and I got a quantity of 2,100 phones. So again, if we're charging $50 per phone, we will sell $2,100 each month, right? Again, we can interpret that in the demand model. If cell phones are being charged sold for $50, then consumers are willing to purchase $2,100 each month based on this model. All right, now letter B says determine the prices for which quantity supplied would be greater than quantity demanded. All right, so we're going to solve this inequality. So I'm going to set supply to be greater than demand. I'm going to do the same thing I did on the prior slide. I'm going to add 15p to both sides. I'm going to add 900 to both sides. And then I'm going to divide both sides by 75, and I'm going to get p is greater than 50. So if p is greater than 50, then supply is greater than demand. Right, so again, our interpretation here is that if the company charges more than $50 per phone, then the quantity supplied will exceed the quantity demanded. So we're going to have an excess of phones, right? So there's fewer people buying, right? The demand is smaller, so there's fewer people buying than there is phones being supplied. So we're going to have excess in inventory. And letter C says graph the two equations. So if we were to plot these lines by hand, this would be pretty easy to do, right? Here's what our two graphs look like. And we can see that here's our supply equation right here. And then here's our demand equation right here, right? So here's the equilibrium point that we found. So on part A, we found the price of 50 being the equilibrium point and the demand or supply of 2100, right, corresponding to that equilibrium point. And we can even see from part B, if we charge down here on our x-axis, right, our p-axis, if we choose more than $50 and we come up here, supply is greater than demand. And that was what we got in part B, right? Again, if we're choosing more than $50, right, we're going to see supply is greater than demand. And so that matches the solution we got in part B, matches visually. There's our excess. We have more supply than we have demand. We have excess inventory, right? Now, even though the problem didn't ask this, right, since we have the graph, we could talk about it. If we go less than $50, if we charge, let's say, $40 per phone, we're going to have a higher demand than we will a supply. So we're going to have a shortage in that case. We're not going to have as many items being supplied that are being demanded by the consumer. And so that would be a shortage. So in the most simplistic models of business, things tend to move towards equilibrium, right? So in other words, if we're in a shortage, if we're charging $40 per phone, again, that's a really cheap phone. Please help me find a phone that's $40. But in this model given here, right, if we have a phone where we're charging $40, what's going to happen is we're going to have consumers demanding product that the suppliers don't have out there. So the suppliers are going to want to supply more to make the consumer happy. So what's that's going to do is drive the price up. And that's going to charge more, right? Anyway, all right, so this is the last example here of our linear functions, right? Make sure that if you have any questions, you post on the discussion board in Blackboard, and we'll see you in the next section.